Let's look at some polynomial theorems that can save us some time. Because polynomial division's okay, but it can be time consuming depending on the size of the polynomial. So first of all, the remainder theorem. If we're dividing by a linear factor, then great. All I've got to do is substitute a into the polynomial. We find out what the remainder is straight away. I don't have to do the whole division. Let's just prove that. So okay, there's our algorithm, but now we know that the divisor is x minus a. Now, it's simple enough now. Let's substitute in a, and a minus a, of course, is 0. And that leaves me with polynomial a is equal to remainder a. Now, I want to show that it's the remainder x, not remainder a. That, in other words, it doesn't matter what I substitute in, I'm going to get the same answer. But that's fine because, remember, the degree of the remainder is less than the degree of the divisor. Well, I'm dividing by something with a degree of 1. Therefore, my remainder must be degree 0. It's a constant number. So it doesn't matter what I substitute in, Rx will be that constant number, which will be the remainder for our polynomial. So now, let's find out. It's the same one, I think it's the same example we did, but just to show that it does work. Substitute in 2, bingo, we get our answer straight away, negative 19. Now where it's really useful is actually when instead of calling it the remainder theorem, we call it the factor theorem. So the specific situation where the remainder is 0. So if I substitute a in, get a remainder of 0, it must be a factor, there is no remainder. Now that's a very useful thing. So we're going to show that x minus 2 is a factor, hence go and factorise. Sub in 2, what do you know? You get 0. Alright, so we now know x minus 2 is a factor. Well, I've got to factorise the whole thing. I need the other factor. It seems silly now because I'm going to end up doing the polynomial division anyway. Let's carry out our division and eventually we'll end up, there we go, remainder of 0. So it sort of defeats the point. I've ended up doing the polynomial division, came up with 0. So why use the factor theorem in the first place? Because if I'm going to get it by the division. Alright, well, let's finish off our factorisation. X squared plus 2x minus 15, x plus 5x minus 3. So the reality is I don't do the polynomial division. I know it's x minus 2 times something. And then we just use a little bit of logic here. I know that the leading term times the leading term must give me the leading term. Therefore, x times something must give me x cubed. So it's got to start with x squared. But the same at the other end. The constant times the constant must give me the constant number. So negative 2 times something will give me 30. Okay, well, I know it's negative 15. Now I just have to worry about the term in the middle. Well, if I was to leave it like this, how many x's would I have? Well, there's only one combination there that's going to give me x's, and that's minus 15x. But I don't want minus 15x. I want minus 19x. So I still need another negative 4x. Where's it coming from? It must be coming from this missing middle term that I haven't got yet. So negative 2 would be multiplied by that missing middle term. Okay, well that must be 2x then. Bingo. I haven't had to do a whole polynomial division to get it. And then I just complete the factorisation like I did before. So now, here's a cubic. We're going to factorise it. This time they haven't given me a hint. So, yes, I could pick random numbers and see if they work. But obviously they're sensible numbers to pick. Remember? Constants must go into the constants. So it makes sense to choose factors of the constants. Now, I purposely picked a number here which has quite a few factors. So it might be 1, 2, 3, 4, 6, 9, 12, 18, or 36. But of course, it could be a negative number. So now I've got all those. But hang on a sec, this is not monic. So I've got other things that are possible. Fractional factors. Because you might end up with, say, 4x plus a number, which would give you the solution x, we'll say it was 4x plus 1. 4x plus 1 would give you the solution x equals negative a quarter. And so negative quarter is a possibility. Anything that's in that form. Factors of the constant divided by factors of the leading coefficient is a potential solution. So all of those numbers, but now I could divide them all by 4. They're going to be possibilities as well. Now some of those I've already done, because some of those turn out to be whole numbers. So 4 over 4, 12 over 4, 36 over 4, we've already talked about those possibilities. But all those other ones are potential solutions. And, well, hang on, 2 goes into 4 as well. So all of those possibilities divided by 2 could be a possible solution. Again, we've got some double ups there. So 2 over 2, 4 over 2, 6 over 2, 12 over 2, 18 over 2, and 36 over 2. Oh, by the way, they could be negative as well. So we've got all these possibilities we could choose from. Now, I'm not going to make life hard for myself. Obviously, I'm going to try easy ones first. The logical first one to try is going to be, 1's an easy number to substitute in. But I think 4 is more logical. Sub 4 in. Oh, what do you know? Well, there you go. That was lucky, hey? Okay, that turns out to be 0. No, you're right. Of course, I'd probably check 1 first. Yeah. Okay, I now know x minus 4 is a factor. Now, when I've got a cubic, if I'm going to divide by a linear factor, I know I'm going to end up with a quadratic. And quadratics are easy to factorise. So I'm not going to worry about looking for the other ones. I'll now just look at it and go, well, leading term times leading term, well, that's going to be 4x squared. Constant times constant, that's going to be negative 9. Now, if I was to expand this out, I'd get negative 9x. Negative 9x is what I want. So in this case, there mustn't be a missing middle term. So it must just be 4x squared minus 9, which factorises to be 2x plus 3, 2x minus 3. So in fact, in our list of all our possible solutions, only one of the integer solutions would have worked. I just got lucky. I picked that one first of all. The other ones that would have worked would have been, where are they? There we are. 3 on 2 and negative 3 on 2 would have worked as well. All right, let's have a look at some HSC questions. All right, 2004 paper. They've given us a polynomial, but written a little bit differently. A and B are real numbers. We've got to find B. Well, we've got some other information that will help us. We can use our remainder theorem. So I know polynomial negative 1 will be negative 11. Bang, sub that in, and we'll get B is negative 11 straight away. Now that was the logical one to pick here, because had I put in positive 3, I would have gotten A, 4A, wouldn't I? So I wouldn't have got B straight away. Made more sense to use the plus 1 over there. Okay, so what is the remainder when we divide it by this quadratic? Okay, well now I'm going to use the other bit of information. Polynomial 3 is 1. So now I go, oh well, 4a plus b is 1. But we just worked out b. So therefore I can work out a is 3. So the remainder, well actually I've written the whole polynomial out, haven't I? I've substituted in and got 3x minus 8. But 3x minus 8 must be the remainder. Because we've got divisor times quotient plus remainder. So there's our remainder. Okay, 2002. All right, again we have to find a. Okay, well, whilst they haven't said it to me, but the remainder when I divide by x plus 2 is 3. So I know polynomial negative 2 is 3. There's the information I need. So sub in, and there we go. So that's a nice quick question there. A is 19. Now, this time, we're dividing by a quadratic, but nicely they've factorised the quadratic for us. The quotient is qx, so now we have to come up with the general form. So in this case, the most general form, well, we know the divisor is of degree 2. Therefore, the degree of the remainder is 1, a linear function. That explains why the most general form is ax plus b. How you explain it, I guess, is up to you, but really that's what they're looking for. How do you know the remainder will end up possibly being a linear function? Now, it might not be linear. It might be a constant number. A might turn out to be 0. But what they're saying is the most general form would be a linear function. Okay, let's find remainder 4. Again, we'll sub in what we know. We know polynomial 4 is negative 5, so there's polynomial 4. So remainder 4, we get it straight away, is negative 5. Now, they've given us a bit more information, and we have to go and find the remainder. Okay, so remainder 4 is negative 5. That's what we just found. So 4a plus b is negative 5 when we substitute it in. We've also now been told, well, haven't been told, but we can conclude, so we now can conclude polynomial negative 1's 5. Simultaneous equations, and we got a is negative 2, therefore b is 3. So our remainder, we said it was in the form ax plus b, so minus 2x plus 3. Exercise 10D, I just make a point there with your factor theorem, is what I was talking about before. If it's not monic, the factor, then you might have to substitute in a fractional possibility to come up with. So if you wanted to prove 2x minus 1 was a factor, you'd sub in a half.